That's a good sign. All right, so let's see, 1229. Information. That's good. Let's see. So this, yeah, so that homework 7, everyone did well on it. I guess one group, I kind of wanted you to go back to the pressure equation, the free energy pressure equation that has a log in it, and then kind of develop that concentration and activity. One group did that. I gave them 2 points. And then everyone else just said changing chemical potentials, RT, the activity. and then kind of worked it from there. That was okay. Everyone was able to do this first one, which I thought would be kind of challenging, but everyone like zipped through that. So that wasn't a problem. Like figuring out the situation of crystallizing from solution. And everyone was able to derive equation 4, which is a derivative, then a couple plug in the answers thing. And then everyone was able to figure this out. I mean, it's in the paper. He talks about it. So I think everyone did that. And then and everyone did this. Like everyone figured out 4A and 4B. I mean, it's basically read the paper, but it was a little bit more than that. It seemed like everyone did really well in this homework. There wasn't much to talk about. It's like seemed okay to me. But any questions on it, or all right? Let's bear it down. So yeah, this week we got this metal organic framework business, and then some other things that have to do with that. So and there's like 6, I think. So there's a dissertation, which is, we only have the abstract of it. I think, I don't know, someone last year, I used the same homework last year. I think someone last year found the dissertation, maybe. Like you can get it someplace, but anyway, then this is just like, what is a metal organic framework? So there's a wiki page, and then there's this book here that should be working now. Mark 8, since structure of your applications. This is like a collection of papers or something. I think it's not exactly, or what is it? It's a guy's, it's a Zia. I don't know if that's man or woman, but it's a person's dissertation, not the person from wherever, not the one that's that abstract. And it goes through just all the different ways to make metal organic frameworks, materials. In this paper, they're doing this 70 something MOF 74. Oops. Which I think is part of this somewhere. It talks about this. Maybe that's not the name of it. Anyway, yeah, MOF 74, this thing, which then I noticed he doesn't exactly give a very good description. I mean, so they'll always show these kind of graphics, and they show micrographs that show that kind of structure. How to make it, so this other paper, so how to make it, this seems to be pretty simple. I think this paper. So in the materials section of this thing, experimental methods, they say like, this is how we make it. So you take magnesium nitrate, which you can buy, and it's got water. And you add this dihydroxy terephthalic acid. So that thing is it's what you make water bottles out of, PET. So seems nice. And then one of it. Let's go very good screen. Auto. It kind of made some noises like it was doing that. Oops. Yeah. All right, so it's like the aromatic. So you have like a benzene ring, and then on these two sides, like a pair of positions, you have a carboxylic acid. That's terephthalic acid, I guess. So it's a dicarboxylic acid. If you add a diol to that, like ethylene glycol, then these things make water, and you can react both ends the same way. And these things too end up with a chain of these kind of aromatic ring things. So that's a water bond, basically. Right? It condenses. If you have something that can draw the water off, like if you heat it up above the boiling point, then it drives the reaction. And you can do this also with a dichloride. So you could do a dichloride here instead, and that makes HCl. Right? And then you end up with the ether linkage. That linkage is an ether. Which that linkage is like if you put UV on that linkage can break. That's one thing. So it's sensitive to breaking by UV. And then also, so the oxygen bond, that's a really flexible bond, so it's completely free to rotate. And then this aromatic ring. So this is a planar structure all through that. So it's rigid. The aromatic ring, the sp2 is a planar structure, and if you have it conjugated, so it's double, single, double, like in graphene, then that's all within one plane, and that includes like this carbon too. So there's a resonant structure where the double bond can go here. The double bond can flip around, that's why it's planar. You can flip to the different sites. So anyway, that entire thing is like a card kind of. You can think of it as a card. You know, if you have kind of a card, and then you have these oxygen linkages that are going to make it like cards that can flip around. The molecule is going to be like that. But anyway, so that's PET. But you can also, like if you have silica, and then it's going to have like hydroxyls on it, it looks a lot like that thing. You can just take, so if you have silica, like silica, and the surface of it is covered with hydroxyls, then you can just react it with that, generate water, so condensation reaction, and then you have a metal that's not a metal, but kind of you could have some inorganic, organic framework thing forming from that. So how that forms, so there's other kinds of things like that, like with a zeolite, you can start with, see, when I go back to that. With a zeolite, you can start with, you're going to make SiO2 glass, right? You can start with this SiO, like methyl groups. So silicon's got a tetrahedral arrangement, and titania can also have a tetrahedral. Like one of the oxidation states of titania can be just like this. You can have TiCl4, or you can have, this is an ether linkage. So you can have these ethers. It can be methyl, ethyl, propyl. Right? And the reactivity, so if it's H, then that's a hydroxyl. So hydroxyl is the highest reactivity is if you have chlorine, like SiCl4. That's super reactive. That'll just turn into silica, and they make HCl gas, which is poisonous. Burns your skin, burns your lungs, burns your eyes, burns you. Seriously burns you. You know, it's a gas, but it goes right into water. And you're kind of made of water, so you become an acidified person. And then, so the longer the organic group, the slower the reaction happens, the more controlled, but also the less you kind of reactive it is. So it's harder to make this stuff if you're trying to make silica. Anyway, so you can play around. You can buy all these off the shelf, so there's anything. And the cheapest one is this SiCl4, because that's made from quartz rock, is SiO2, and you just put it into HCl. With temperature, you can make just liquid SiCl4 as a liquid. So you make like liquid rock kind of, and then react that if you want to make these things. So this whole thing is called Sol Gel. And there's a book called Sol Gel Science by Brinker from like the 1990s, I think, that kind of goes through that. So basically you can use that process This is something that's really easy to do. Like you just change there's an isoelectric point for this SiOH. If you get a pH lower than that, so if you make it acidic, it'll react to silica. If you make it more basic than that, it'll react by a different route to make silica. So the isoelectric, it's stable, and then you just change the pH and just make this thing. Then there's also water glass, which is like sodium. It's a sodium salt, sodium silicate. So something like that. I don't know. Anyway, that thing is pH like 14, maybe pH 12 or something. So that one you just acidify, and it does the same thing. Basically, it'll go to SiOH and then finally to SiO2 through some kind of ionic reaction scheme. So anyway, that kind of sol gel was the beginning of this whole thing. So the zeolites that come in nature, which are like mesoporous rocks, kind of like aluminosilicates. So you can do the same routine with Al2O4, right? So you can do precursors of organic metallic aluminum precursors and do kind of the same condensation reaction to get alumina. So you can do titania, alumina, silica, and some of the other transition metals you can do this way too. So you can kind of mix, alumina and silica, and this happens in nature also. Okay, so like in nature, there's these silicates floating around under the right pH conditions, and then they can condense in there's bioreactions that make the same thing happen. It's like when you make shells, it's kind of a condensation reaction of ocean water to make the shell. It's kind of the same thing going on. So there's another branch of sol gel science that just goes to like biogenesis, kind of like how life first formed and how, anyway. So one of the papers here is about that biogenesis thing. So you begin with sol gel science in the 1990s. Then in the kind of late 90s, you get zeolites. So there's a lot of PhDs. There were a lot of PhDs in sol gel science in like 70s, 80s, 90s. And then this book was written in the 80s, I guess. And then this zeolite stuff came around in the late 90s for catalysis, which is using sol gel, but take this TIOS, so tetraethyl, so use an ethyl group, which is less reactive, and then put that in with surfactant, with detergent. The detergent will make micelles. So detergent has a hydrophobic oil group, like some kind of an alkane group, like CH chain. And then the other group would be like a sulfate. So it's got a negative charge. So basically, when you put that in water, these things will the tails will all get together and they make a micelle. So you have this surface charge of the thing, and then so there's a sodium ion associated with that. It's floating on the outside. Anyway, so they'll organize like that. And if you put salt in, then that thing forms a micelle. And if you put salt in, it'll form rods or ellipsoids. And if you put enough salt in, it'll form fibers, like long hair-like fibers that are stuck together with ionic bonds with a really strong ionic attraction. Anyway, so that's like shampoos like that. You know, shampoos basically these kind of entangled worm-like micelles. They also call that thread micelles, or there's some other words like that too. Anyway, so if you stick this thing in, so that was around for a long time. That's the soap industry, soap and detergent. And then this sol gel thing came around in the 90s. Then people took the soap and mixed it with the sol gel, because this is a water system. You're making water in it. So it's usually water and ethanol that you mix to react this in. So you can put a surfactant in, and then you can make the silica form around or you can make aluminum silicate form around the micelles. And the micelles are going to be like 10 nanometers. Or maybe you can tune it to any size you want by changing the alkane chain length. And also there's a wide variety of structures you can make with micelles besides spheres. You can make interpenetrating networks. You can make worm-like micelles. You can make all kinds of different structures, lamellar sheets, basically anything you want. you can make with any kind of structure you want to make. There's a double diamond configuration. It's kind of like a spinodal thing where you have a constant mean curvature interpenetration of two phases that you can make with micelles. So people did that, and then so you could make these high surface area organic oxides, basically silica, titania, alumina, and then that would be like a catalyst support. So you deposit platinum on that if you want. Then say the platinum would stick into your car catalytic converter. And you have like a super, because the problem with it, you want to have like one atom of platinum to react with the gases going through, right? The extra fuel that didn't get burned. And then, so basically, if you have a chunk of platinum, all the stuff in the middle is thrown away. You're not using it. And also, as the catalytic converter goes down the road, Oswald ripening happens, and the platinums cluster together into bigger and bigger platinum chunks, which eventually become non-reactive because only the surface is reacting. So the bigger the surface area you can deposit it onto, say if you could deposit atoms of platinum, then you're like doing pretty good, that's going to work pretty well. So it's basically the idea is like the highest possible surface area you can get. And with some of these things, you can get like 1,000 meters squared per gram. So 10 football fields in a gram. And you can produce these on an industrial scale. You can make trainloads of it. So the catalysts are used up. Like you think of a catalyst like, oh, it's going to run forever because it's not consumed in the reaction. But in an industrial reaction, the catalysts wear out quickly. And they're like the most expensive. Like if you're making polyethylene make it with a titanium silicate catalyst, aluminum silicate titania mixture, Ziegler-Natta catalyst, they call it. So Ziegler and Natta won the Nobel Prize for making the catalyst that makes polyethylene polypropylene, which is basically using this kind of sol gel thing to arrange these metal atoms so that they can coordinate with the ethylene molecule when it pulls up to, or propylene molecule when it pulls up to polymerize. So anyway, so before they did that, you couldn't make polypropylene, and nowadays like everything's polypropylene. So basically, I think it was like the early 60s, they kind of figured out how to do that. So anyway, it's a coordination chemistry, like it holds the molecule in place so that it doesn't, because normally propylene is like that, and this double bond can flip over here, so it's a resonance structure. It can flip between those two. So if you try to polymerize here by opening that bond, the electron just escapes over to that other bond. So you can't polymerize. So see how you distill oil, and then the top thing that comes off is ethylene and propylene. So like you have 50-50 cut. So the ethylene you can polymerize just by putting sunlight on it, and it'll polymerize because it's fixed. Like the electrons there, you can open that up and it makes a carbon chain. But the propylene has this resonance problem that this double bond can flip over here. So you resonate between those. When you try to get that, in order to get that, you have to actually put your hand on it and hold it. And you can do that with these aluminosilicates. And that's what Ziegler-Natta figured out. Ziegler was a diffraction guy in Germany, and Natta was an Italian chemist, organic chemist. And somehow, I think they worked together. The town where Natta actually worked for a petrochemical company, and Ziegler, I think, also worked for BASF or something. So there were different petrochemical companies, though. So I think they interacted to do this together, but Natta characterizing the structure of these crystals so that you could figure out which one would work to hold the molecule. And anyway, nowadays, so literally trainloads of that catalyst are made and consumed, like almost every day, right? So it's like, it's a catalyst that's not used in the reaction, but it wears out. So basically, there's a huge industry, and so of this, the propylene and the ethylene are byproducts of petrochemical. Like in Africa, they just burn it. They burn the ethylene and the propylene. They just torch it up because they don't have a infrastructure to pipe it. Like in the US and in Europe, all the stuff from the oil wells, out from the distillation columns, gets piped to all over. Like polyethylene is produced in Chicago, and there's no refinery in Chicago. Well, there's one in Evansville or something, I think. But I mean, in Gary, Indiana. But basically, all the ethylene they're using there comes from Texas. Comes on a pipe. and they polymerize it. So in the US, we collect all those gases. Anyway, so all this solid gel stuff and this kind of all that stuff is related together, and the MOFs and the zeolites are all kind of in the same family of mixing organics and inorganics together, making something new, something different. And also there's this biogenesis edge of it, that life itself was probably created by some kind of a templated synthesis of this kind where you made like shells and things. And then the shells themselves templated proteins. I mean, people think that. So there's a thing about where life came from that has something to do with shells and proteins, you know, and through this kind of solid gel reaction. So that's the last paper of this thing. Anyway, so it's a pretty rich area. There's nothing to do really with thermodynamics, except that these people are doing they're doing thermal analysis, right? DSC, and then so there's different kinds of calorimetry. So you want to measure the enthalpy of a reaction. So you're going to have so it's going to raise the temperature, you know, the heat capacity, then you get the enthalpy that happened by the temperature change. Temperature change times the heat capacity gives you the enthalpy. So if you have, so one way to do it, the normal way to do it is stick your stuff into two cups, two actually platinum cups usually, and then weigh the material that you put in. One's empty, and then you can ramp the temperature up and see how much heat it takes. So you're putting heat into both of them. There's a differential heat between the two that you put in, and when you go through transition, it absorbs heat. In other words, the electricity you put in to heat it, you can convert to energy. So you figure out how much extra energy it took for the thing that had stuff in it versus the one that doesn't have stuff in it. And from that energy, extra energy, that's the enthalpy of whatever transition, melting, or in this case, they're releasing water from a MOF, from a metal organic framework thing. So that's one way to do it. The problem with that is they're having a problem with that technique because it's not very sensitive, number one. So you need a microcalorimeter. And number two, there's a problem that any amount of water, this particular MOF, this MOF 74, any amount of water just sticks to it. So it has to be an ultra dry environment in order to do that. Apparently it's hard to do it with zero amount of water, absolutely zero amount of water. And they're trying to measure the absorption energy of water into the MOF because that's the problem with using it. So anyway, and this MOF they're going to use to pull CO2 out of a power plant, out of a coal plant. They're going to stick this, like train loads this MOF into the exhaust pipe of a coal plant. The MOF is going to eat up all the CO2. They can bury the MOF somewhere. I think that's the general concept of what they're doing. You know, so that turns out when you have a combustion, there's no, like you can get rid of the oxygen and stuff. So you can basically just have almost pure gases if it's a high enough temperature combustion, right? So anyway, so to get these enthalpies, instead of using like a differential thermal calorimeter or a thermal gravimetric calorimeter, there's like two types of this kind of heat thing. There's a bomb calorimeter, which means you just throw it literally into a bomb. So a bomb is going to be like a metal chamber that's closed, and then you put something in that explodes in it. And then if it's a bomb like in war, it explodes and sends the metal shreds out and kills everyone. Or bomb calorimetry, you just measure the heat of the big metal thing. So you stick it into this bomb, it doesn't blow up. It does blow up inside, but it doesn't like send shards around the room. And you just measure the temperature change of the thing, like when you torch it, basically. So I guess that's what this paper is about. Is using a bomb calorimeter to they don't call it a bomb calorimeter, they call it like a something dropped something or other. But I think the idea that I get from it is that it's a bomb calorimeter. Like it's just an enclosed thing and you do the reaction inside of it and then you measure the heat that comes out. They don't actually describe the machine. They give the name of it. It's like a drop, something drop combustion, flue gas, blah, 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 work sensitive, blah, 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 acid base, thermochemical, blah, blah, blah. Dropping device developed initially for study of actinide materials, totally water-free, only drop combustion calorimeter. They don't show a picture of it. I didn't look in the reference 19 to 21, but basically I think it's a bomb calorimeter of some type, right? Where you have it enclosed and you blow it up somehow. They can get the heats of these oxidation reactions, like take their MOF. How do you make a MOF? So how you make a MOF, the advantage of MOFs is that like they're really simple. They just take the magnesium nitrate, some water, you buy that. Then this thing, precursor to PET, to water bottles, dissolve the mix. That's a liquid. That's in water, so that's a liquid. Dissolve it. You put DMF in, which is kind of a nasty solvent. This is what they closed down Jude Euro's lab because he was using DMF. But DMF, the only thing I know about it is if you have, I had a screwdriver on the table and like a couple drops of DMF, and the whole screwdriver like just dissolved, like the handle that normally is impenetrable to anything, just is like a puddle screwdriver, and just the metal part is left, So I'd imagine it's not good for you either, probably, But anyway, it's a solvent. It's a pretty common solvent, so they use that. And then ethanol, which is what you drink when you go to the bar, and then water, which you drink otherwise. Sonicate it, right? Screw cap jar, stick it at 125 or 26 hours. That's it, done. Filter that. It's like so simple, and they're going to end up with these this stuff. Like literally, you end up with stuff like this. Like you do an SEM. This isn't even TEM. You SEM, you get this infinite array of these perfect things, whatever. So I mean, that's the appeal of this, is like any idiot could do this, apparently. Maybe not any idiot, but almost any idiot could do this. I know some idiots that couldn't do this, but basically almost anybody can do this, right? You could do it in your bathroom probably if you wanted to. And then you have this MOF. I'm not sure what you're going to do with it, but basically you have it. I mean, if you happen to have a coal plant, I mean, you could do this on site at the coal plant. Like you could make the MOFs. You could literally make the MOFs almost in the flue gas, Like you'd have a room right next to it and just dump it in, have a conveyor belt that just dumps it in. So it's simple to make. And then you get these kind of elegant structures from it. So it's appealing to people, to like someone that's a chemist. So this Alexandra Brodsky is like hopping all over the place, and now is at Peter A. Ruck Thermochemistry Lab at Davis School of Molecular Sciences, right? And then goes to and then ends up at so that already is like a little bit odd, right? I mean, it's not, it's a little bit of a like an odd place. And then she ends up at the Center for Materials of the Universe, okay, Arizona. I guess that's it. And then School of Earth and Space Exploration. So this is like, how do these MOFs form? Are they templates, the structure directed agents to form life? Like how does life form originally? How does it form? It involves MOF somehow, right? So that's like we call moving around. I'm sure her pay increased and she went to the Center for Materials of the Universe. Maybe she's head of it, it's hard to tell. But so it'd be interesting to see her life story, actually, to see like how it went from one thing to another. Because apparently, if you look at her papers, which is a few of them in here, it's all about thermal analysis, like DSC. Like just that's almost the most banal thing you could possibly do, right? And then she ends up at the whatever whatever that's called, the Center for Materials of the Universe. It's like there must have been a series of steps that reached to that, Anyway, it's kind of interesting to see just in terms of career development, like how that works. Anyway, so storage gas described in the dissertation's abstracts. This is just like what MOFs are, and there's that book on what MOFs are. And then give a description of what MOFs are. So there's a wiki page. I mean, I don't really have a really firm grip on how this thing works. Like, in other words, you get this perfect structure. If you go to that wiki page, which isn't on the web page, but and why is it a secure website like HTTPS to get to Wikipedia? It's kind of odd. Like, anyway, maybe everything's secure now. I think it's just moth. It's probably the first thing. Oops, what did I do? Yeah, so basically this is a, I think it's, so the resolution is 10 nanometers. I guess that's TEM. And then this is the moth, and then there's the picture of what it's supposed to look like, and it's exactly the same thing. And it's just this little simple cook step that we in the paper, right? You just do that cooking, you stick it in the TEM, you get that. I mean, I'd be pretty excited if I got that out of that little one-step procedure, you know, with two common chemicals, like things. So, and then so you can see, like, if you have this terephthalic acid has like two functional groups and kind of naturally form like a chain, right? So you could have a 1D, and you could, instead of putting a diol in, you could put in like a silane that's got two of the tetrahedra blocked with organic groups. Then you could have a 1D moth. You could have like, it would be an organometallic, basically polymer. But then, so he's saying like dimensionality inorganic, dimensionality organic. So if you could make, so that on the aromatic ring at the center of terephthalic acid, there's 6 sites. So you could have potentially 6 carboxylic acids sticking off. So you could have a 6-fold, make a 3D structure with it if you wanted to. Or you just need to have 3 of them. You'd have to have 3 sites. So you could have a 3D, or if you did 2 of them, because it's planar, it might make 2D. If you did 3 of them, it might make 3D. So your organic can be 0, which would be just 1D. Like, you know, it's only got 1 carboxylic acid that reacts with a metal. So you just have a metal organic cluster. That would be a 0, right? Both are 0. Or you could have a 0 and then combine the 0 with 1, 2, or 3 inorganic dimensionality. In other words, silane has 4, so you could block off 3 of them, and it would be a 0 functionality, or block off 2 of them, then it would be a 2, then would be a 1, like a linear. And then if you had 3 of them, it would be 3D or whatever. So anyway, you could potentially get like 1, 2, 3 dimensional or 0-dimensional objects, either with the organic or with the inorganic, but basically not necessarily both, right? In other words, you can't get, if you combine a 3D polymer with the 3D inorganic, apparently you get gunk out of that. So those boxes are left empty. I think it's hard to imagine how that works, but anyway, so the idea is like you can play around with dimensionality with this thing if you want. Like, this is a planar structure, apparently, that's in the TEM. And then I don't know, they go through a few things in here. They go through some of the applications for it. I'm not sure how many of these have reached fruition, you know. Like, there's a lot of talks, it's a lot of proposals and PhDs. I'm not sure how many, I don't really know how many are in industrial use. It would be kind of useful to see that. See, have been explored for. Oh, and then some of them can have these features that she mentions in her paper here, wherever that is. All right, so, right, homework 8. I think it's in this dissertation. And then I can't search this thing, I don't think. It's called, what's it called? Ferry. And this is, you can have an interaction between a magnetic and an electric material, so that you can turn the magnetism on and off with an electric field, or you can turn the electric conductivity on and off with a magnetic field. And you can do the same thing with light. So you have like 3 things you can hit the material with, and it's possible with these MOFs to tune it. People claim that they've tuned it so they can get these magnetic, electronic kind of devices almost from this kind of structure. Right, so there's some kind of unique features that they get from MOFs. In that dissertation abstract, she mentions that, and then in this thing they mention it someplace in here, like hydrogen storage. biological sensing, electrocatalysis, drug delivery, nuclear waste, which is like research money, biomimicry, that's that last paper, desalinization, multiferrics, which is something I never heard of, but basically this sounds like something that you can get a research proposal on if you want, right? So ferroelectrics, it means, so you can have basically, it's just saying like the electric field can turn the magnetic field, like a ferromagnetic material can be made ferromagnetic or paramagnetic by changing the electric field on it. And by tuning these MOFs, you can get that. I'm trying to give some example here. There's some references. It's a lot of references, like 222 references in this thing, but anyway, you can glance at that if you want. There's that book in there, you can look at that if you want. Basically, limit this to one paragraph, just like whatever you think it is. Probably there is not a wrong answer for that. Then there's like, so there's that, which is actually like 3 books, a book and a wiki page, and the abstract to that dissertation. So that's like 3 things just for this. Then this thing, thermodynamics drives the stability of MOF 74. This is that paper, this paper, the MOF 74 thing, with the bomb calorimeter. So this kind of gets to the point of like when we first started this chapter, before the d orbital stuff, there was just like Hess's law, right? Someplace here, like how you add up the enthalpies, right? So how do you if you can, so here they have a tool, this bomb calorimeter, like they want, so how do you add up the enthalpy to go from, you have a hydrated MOF, you want to dehydrate it and then maybe use it to absorb water or use it to absorb CO2 or something. So if you can take this thing and it has water in it and then torch it in a bomb calorimeter and get the heat of that reaction, and how many of those things you have to do to get the reaction that you want, which is your metal organic with the terephthalic acid goes to the metal organic terephthalic acid plus water, right? So somehow what they start with is the bottom thing, like metal organic, the MOF, M2, and then this is the terephthalic acid with hydrated with 2H2O, then they torch it and then they can get this thing, right? So that's kind of the idea. So I think some of these are run backwards. Here's the metal organic plus oxygen goes to something, and then this is metal organic plus oxygen goes to something else, I guess, 3H2O. So this is a mono dehydrated, tri-dehydrated. And then like just the enthalpy of the heat capacity change in the metal organic and the heat capacity for water. So those 2 things you can look up, right? I mean, you can find the heat. Maybe you can't get the heat. You can measure those 2 anyway, either with a DSE or with their GOM thing. And then once you get all those, and you do Hess's law to add the stuff together. That's the idea. So the question is just go through what they did. Like what? So go through what they did, and then when we did this, we ended up with this long scheme of things, right? Like we had the lattice enthalpy, the atomic enthalpy, the ionic enthalpy, the dissociation enthalpy, the electron gain enthalpy. So we had all these terms, right, that supposedly give you the heat of formation for something. And the heat of formation here is like water combined with a MOF, right? So the question is like, is this scheme, which is useful in a computer program, because you can quantify all these components in a computer program and mess around with them and change the heat of formation. Like you can simulate that, right? So this is kind of written for coding in a sense, like the way it's broken down. So how does that match up with this scheme? Like where is the lattice enthalpy? In other words, where are those components? Like here, they're doing experimental measurement to get these numbers, and they add in the numbers. That's Hess's law. I mean, in other words, if you can get individual steps and add it together, you should be able to disassemble this thing into the same way this is done. So like, where of those series of steps, where is the lattice enthalpy, and where is atom, where are all these components in that thing? Or does this have nothing to do with what she's doing? She's just, this is like a brute force method that she's used. And then this is kind of a more finesse thing that you might use for a computer program. The two things should be the same thing, right? So where is the lattice enthalpy in this thing? Like, how do you find that? Like, where is it?
So you said the reaction at the bottom is the one.
That's what they
in their
want.
methodology that they started with.
That's the one they want. They want to know like how to hydrate, how much enthalpy is there to hydrate this MOF, because they want to get rid of the water in the MOF. They want to know the enthalpy of that. And they want to know if they change the M as a metal, if they change that metal, like, is changing the metal going to help the situation? Like, so, and if the enthalpy is lower, it helps the situation. Like when you get to the last paper, which is that bio thing, whatever, this prebiotic, the conclusion here, and it's the same author, the same PI of it, is that the enthalpies of these reactions, these hydrolysis condensation reactions, is so low that things like, just if you have a protein present and it can guide the ceramic, the inorganic and the organic molecules to come together in the right way, that's going to be a lot more influence than the actual enthalpies of the reactions. So it's like, maybe that has to do with the MOFs too. So in this case, she's arguing that all that enthalpy work that she did doesn't make any difference. It's really this idea of a structure directing agents. In other words, the hand of God, I think, is something similar to a structure directing agent. There's always anytime you get into this biology, whatever, there's some kind of religious aspect to it. But so anyway, the structure directing agent, which I think of as a finger coming down, with a lightning bolt on it or something. But anyway, so anyway, is more important than all this stuff here, So anyway, question. So they're playing around with small numbers in this thing. Like, you can't measure it in a DSC, this dehydration. You need to use a special calorimeter thing to get it. So what was the question? That's what they're trying to get. Yeah, the last equation is what they want, and they're getting it by adding up the components, like Hess's law. But then I guess part of the question is, where does our scheme fit in with that? Like, we're here too. It's like, where's our lattice enthalpy? Like, we want to know that within our framework. So anyway, so it's like, what role is lattice enthalpy? And then the bigger thing that's going on here is the entropy. And whenever you have water, you have to think about entropy. So the water, it's a large number of small things. And the organization, when they organize like in this MOF, like you can see the TEM, there's a lot of organization of stuff. So entropy should play a huge role in these things. Like, you got this perfect structure forming over large distances, right? So the water molecules and something like that are just totally organized, like a crystal, like ice. So when they break out of that, if you dehydrate this, they gain a lot of entropy. I mean, it's a lot higher entropy once they leave this thing, right? So where is that entropy in this scheme? Like, where is it? That entropy is like so big. They're talking about dehydration of a perfect crystal structure when the water's organized, going to disorganize. Where is it when they do this simple brute force thing? Like, it's in there somewhere. I mean, these things are in there. It's just like, look at it from that framework. Like, they aren't considering those things. So where is that stuff anyway? And this thing, this is another paper, not about this is about perovskite. So perovskite's, it's kind of similar, So it's a metal organic, but it's not a MOF. So MOFs are porous, and perovskites are actually just crystals. They don't have pores on. So I guess that's the main difference. So anyway, they're playing kind of the same game. This is that book, right? And then Heat of formation for perovskite. So it's the same author, this Alexandra Navratsky. And guess what? It's like the same thing. Like here's the enthalpy, there's the final reaction. It's like, it's kind of like if it worked once, do it again. Yeah. So I'm not sure if this is before or after the other paper. So 2019 and the other one, the other one's 2020. So this came after that one. So she's doing perovskite, which is also another like popular, and within the same framework, like, so you take this, these salts, right? Cesium, lead, iodide, salt, and then so there must be a methods thing at the end of this too. No, this is a Jack's paper. I should have a methods in it somewhere here. I guess it's just a letter, right? Jack's is like letters, so they're short. So it should say how she makes it. This is supplemental. But I think the way to make these perovskites is really simple too. It's basically just put the stuff in a beaker, heat it up, and you can see the crystals, makes a solid crystal and just crystallizes out of the solution. Right. So you have, so that's a really simple thing. This is also like simple chemistry. So she's attracted to these simple chemistries that make complex structures, apparently, and then anyway, so, and then she gets these heats. This time she's using a DSC. So this is a not typical DSC. So you have your two pans, and then you get extra heat into the pan that's going through a transition. So you can see, and you take the differential heat between the pan that's got something in it, the pan that doesn't have something in it. If you go along as zero, they're the same, and then you get to that transition, and boom, it absorbs a bunch of heat when you melt the crystal. Right. So from that melting point and from diffraction, you can tell that you made the perovskite. There's diffraction here somewhere. Yeah, there's a diffraction patterns that shows they made the perovskite. And then this is the enthalpy of melting it. And then they see thermograph, then the thermic peak appears, whatever. So they're getting these enthalpies from a normal DSC. Maybe it's a microcalor, like a small one that can measure small changes in heat, but I think it's just a normal DSC. Then the solution calorimetry, temperature solution, and differential scanning calorimetry. So solution calorimetry, they can run the reactions. It's the same idea, except you aren't heating anything. You're just watching a reaction happen and looking at the temperature change. Right. So basically that's just kind of like the bomb calorimeter. Just look at the temperature change, the heat capacity, and you can figure out the heat. And then this is actually running through a transition, DSC. So, I mean, you guys have definitely used DSC at some point or other. There's a bunch of them around. So anyway, this is the same scheme. Like she's got that breakdown of the thing, and then making a perovskite. It just says like why these particular perovskites. So it's got a band gap. So between the conduction band and the valence band, 1.73 electron volts. So it can absorb exactly that energy, quantized energy, right? And that's happens to be exactly where the sunlight is, the peak of the sunlight. So it's a perfect match for absorbing sunlight to make electrons. And then this for that material in these perovskite solar cells, you have titania that once you make the electrons in the perovskite, you get excited electrons in the conduction band, then you transfer those to a semiconductor, the titania, and that conducts it to the electrodes. So basically, you have the transfer with the titania network, which is white paint, and then you have this perovskite thing that you just cook. Basically, the perovskite's the same process. You put in a salt, you put in some, you put in ammonia, and it just forms a crystal. You just cook it, and it precipitates out. In this case, it precipitates out, and the other one, it also precipitates out with the MOFs too, but it has a porous structure in MOFs, and this is a solid crystal, right? That you can make small, just basically paint the titania particles with it. And then it absorbs electrons, transfers to the titania, and then you make a solar cell with it. That's the simplest kind of solar cell, all room temperature. I mean, because the alternative to make silicon metal, you have to start with silica and then reduce it. So you need a reducing agent like the Ellingham diagram thing, like carbon or some other magnesium to pull the oxygen off. That makes pure silicon metal, and then a chemical treatment of what you get from that. So it's a long process, high temperature process to reduce the silica to make silicon, and the chemical process to purify the silicon to 100%. Then dope it with boron and phosphorus to get P and N. It's a high energy process, really high energy, and takes a lot of time. Making a perovskite is like an overnight thing in a beaker on your desk, right? It's just like almost nothing. And the titania, again, you just torch up TiCl4, tickle, and you just make titania, white paint, basically. So both, all the parts of this can be made easily. You can make train loads of it easily, right? So anyway, so that's the idea of this perovskite thing. So they're trying to just figure out, I'm not sure what they're trying to figure out in this. It's the same thing though. It's like a reaction, and the question is the same thing kind of. Table 2 shows the thermodynamic cycle, calculate the alpha. Oh, there's two phases. They want one phase, not the other. And then logic of the cycle, the values, and the same thing, like where's the lattice enthalpy in this? Like where is it? And that, so their brute force method, where are these components, at least the lattice component of the thing? Because they're talking about the same material, two different crystal, like an alpha and a gamma form, or alpha and delta form. So it's the same chemical composition. The only difference is the lattice, right? So somewhere in this calculation is the lattice enthalpy. There's a lot of numbers here. So where's the lattice enthalpy of that? That's the main difference between the two. Right? They want one, and the one's good, one's bad. So I think one is perovskite and one is, or what? Let's see. This, they show the two perovskite structures here somewhere: orthorhombic and cubic. So the perovskite can go through this transition of structure, and so it's an enthalpic transition. So basically, they're measuring that enthalpy. Anyway, it's hard to get into Jack, so this is of high interest. In other words, 2019, this was like one of the top things people were interested in. So the 18th paper, or whatever here, large scale screen hypothetical. Okay, so this is a different group. So these are like experimentalists, and this is a simulation person looking at the same thing, MOFs, right? And then their point is, so these guys are focused on this MOF 74, like the most popular one, and this perovskite, which is like the most popular, whatever. And the point of these guys is they want to look at everything that exists in the world. They want to say, like, let's predict what kind of metal organic frameworks you could make for hydrogen storage, something like that, like, or separation of CO2 or whatever, right? So they're going to take, right, so it's kind of interesting. It's along the same subject. So they're along the same subject in the sense that they're screening of MOFs. There's also a paper on explosives in there, but anyway, it's kind of a garbage kind of stuff. So they can't do molecular, like they can't do electric state calculations and simulations to get these things because it's too many. They're going to have 137, 138 hypothetical MOFs. So, and it takes a year to do one simulation of one of these. So instead of doing those simulations, but they know there's 300, there's a fixed number of building blocks for it. In other words, there's only so many metallic groups you could use, and there's only so many organic groups you can use. And you're going to match those up, and they can kind of get the fundamental shape of those groups and the interactions that those groups could have with other units, you know. So so basically, they're going to just take the basic concepts of those groups and turn them into what they call Lego blocks. So just turn them into like blocks, then they're gonna take those blocks and see, and then let it cook through a kind of a Monte Carlo simulation to let those blocks form MOFs. In other words, these things self-assemble. Like somehow all you did was pour it into a beaker, let it sit for 26 hours at 127C. That's it. And it just formed that perfect structure. Right. So why did it form that perfect structure? Nobody seems to answer that in the papers, right? And these guys don't know either, but they know that of the possible 300,000 possible MOFs from the 200 different whatevers and the other organic things. So they can throw that into a computer and let it Monte Carlo, like test each one and have it be able to get over potential barriers with rolling the dice and finally form whatever kind of what they call equilibrium structure it's going to form at whatever temperature you want, right? And they can do that quickly, like basically in a day or something. They can just do that for each of these, right? So or maybe less than that. I mean, it depends on the computer, right? So that's what they do. So this is like amped up a little bit higher than the Jack's paper. So Jack's is like level, I don't know, it's probably got like 30 citation index, something like that. And the Nature Chemistry is going to have like 100. So this is like level 2, put it into high gear. So this is, and it's just like doing simulations of using this Build-in-Brock model, like saying that you don't have to worry about any of the details of what's going on. Just have these bricks with certain kind of interactions, let them go through a kind of a trial and error thing to see what they'll make. And they make MOFs with it, and they predict a certain MOF that already exists, and then this is the same structure, right? This is the terephthalic acid, except this isn't the para. So you can have this carboxylic in the opposite one. That's called para, and this is like ortho when it's here. So there's 3 sites. It can be para, ortho, or meta. Let's see, para, meta, ortho. Ortho's the one near, I think. So anyway, the para one's the normal one to make water bottles. And this would make like a planar structure, I guess, if you have this kind of terephthalic acid with these are all conjugated. So all these rings are in a plane, and these carbons that are attached to it are also in a plane. So that entire thing is a card. And it's got this thing can spin around on the sides, right? The reactive group can spin around, and then apparently it's reacting with this, what's that called? I forget the name of that structure, but basically it can react with that and just generate this MOF from it, right? So they predict one that works, one that's known to work. So anyway, the question is in this MOFs and potential, methane storage, blah, 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 using our LEGO approach, then calculate methane absorption. Oh, then they build the structures and they calculate the methane absorption. So they do another simulation where they take their simulated MOF and stick simulated methane onto it and see how it absorbs. Right. And they have some that they know work. Okay. Okay. All right. Thanks. Oh yeah. All right. Can I pay you for this? Or I mean, all right, thanks. That's pretty good. Yeah. All right. So anyway, all right. So anyway, so they calculate the methane absorption. So they do that in the paper too. And they show that one that exists is good, and then it's an ad hoc. So it's just like what they've done is they've taken this kind of idea, like we could use Hess's law, we can use all this stuff to build up crystal structures and figure out what's going on, the d orbital things. And they've said, oh, forget about all that. I'm just going to make bricks. And I'm just going to say like the bricks have these functionalities. And that's it. And there's no lattice enthalpy. There's nothing. They've completely thrown out anything in this course, right? There's no course. It's just like, I can just make this into a video game kind of thing, and that's it. And then I can get the answer. Right? They have there's no breakdown of anything into anything. They just have bricks. That's it, right? So that's kind of an insult to the book in a sense, So if you believe in the book, you should try to defend it. If you don't believe in the book, you should try to say like, yeah, they're right. Ad hoc means they're just winging it, and then the calculation enthalpy of formation is useless. Crystal structure relies only on geometry. And then on the other hand, Novendra, whatever, that dissertation basically said everything is the crystal structure and enthalpies, right? So the question is like just to compare the two and come up with some kind of opinion about either why the Nature paper is the best thing ever, or why the Nature paper is bogus. Like kind of look at it and say which way you think is the right way to go on it. I mean, there's some merit to it, or it wouldn't be in Nature. On the other hand, like everyone else is doing these intricate studies, figuring out experimental methods to measure the enthalpies of formation, then trying to calculate these slight changes and things. Right here, these guys just throw a hammer into the thing and say, like, we can just get everything from this. So it's kind of interesting how things are going, right? So that's one thing. So there's a lot here. So that's, and then there's what that other paper on this kind of life thing where she says she also herself, who's the person who's an experimental DSC person, says that the difference in enthalpy in the polymorphs is less than 15 kilojoule. Like it's near the thermal energy, so it doesn't make any difference. All this enthalpy talk is worthless. And the only thing that really matters is that you have a structure determining whatever, the hand of God, basically, the SDA, that can overcome anything by organizing around biological molecules and everything comes out right. So that merits some kind of comment too. So the last two questions are like people throwing rocks at the whole chapter, enthalpy of formation, pulling the rug out from under it. And then like, what do you think about that? You know, like how, maybe just think about how it all fits together. That's all. Like there isn't necessarily a right answer to the E and D unless you don't say anything, or unless you. So you could read the thing and side with them and say that they're right, or you could argue against it. I guess arguing against it would be the more challenging thing to do. Like if you argue in favor of the class, that would be more challenging. But if you want to just say like what they say is right, and the class is a waste of time, that's okay too. You can just build Lego bricks and like be happy with that. It's not like anybody's actually producing anything here. That's one thing. They're all frameworks of understanding. Like so far of the MOFs, I haven't found any commercial application of MOFs. Zeolites have huge application for catalysis. The perovskites seem to have potential, and they've made solar cells, but there's no commercial perovskite solar cell. Right? There were dye-sensitized solar cells, and all the companies went out of business because the Chinese undercut with the silicon. Like the Chinese subsidize the silicon industry for photovoltaics, so the price is way too low for any other technology, even if it's a cheaper technology or better technology. So there's a lot of technologies waiting in the wing. The thing is, a patent is only 17 years, so you can only wait so long. Like you patent the perovskite solar cell, and it's already been like 15 years. You got 2 years left. Are you going to build a factory to do that? And then the Chinese will undercut you there too, because they can just churn out a factory and way faster than you can. And if they need to switch from silicon to perovskite, they can kind of do that overnight, maybe. I mean, they'll feel the hurt because they already have invested in that silicon technology, but they can handle it in the autocratic society they have. They can handle that. They can just say, let's do this. And then they just do it, So there's some advantages to that kind of society, I guess, in the end, especially mixed with capitalism. So anyway, all these issues about these new materials, like you're researching, hopefully, it comes down to some kind of other issues, So it's hard to tell like where things are going to go in terms of like, everyone seems to think they have the next answer to whatever, but it isn't exactly always that way. Anyway, so that's that homework. There's a lot of papers. So any questions on that stuff? It's a lot of stuff. It's all mixed in, and it's Yeah,
So basically, the main reading is the guy's dissertation, but
that's just like a one page. Yeah. Oh, it's actually, it's
We
more
only
than
need
one
this-
page.
we only need the stuff in the abstract.
No, you need all these things. Yeah, so there's like a ton of reading stuff to do. You can't do all of it, so you just have to spool through it. All right, take the question and then read the thing. Maybe that's the way to go. Like the question's giving you a framework, like she's claiming this, and then we're saying this enthalpy thing. So just read her thing and see what justification she gives for not using enthalpy things. If it's too much, let me know, you know.
Do a lot of control F word search.
Yeah, that's fine. Yeah. Yeah. Control F is good. Just it's just to give you exposed to some of the different things, you know, and how it's got to do with thermo. It's got to do with this enthalpy of formation, but it's kind of the so
Question D, where you said that what was discussed in class. I'm curious as to, because from your explanation, I think you explained the Revendra and the other Lima. So I don't know. Is there any other one that was discussed in class?
well, I mean, so Wilmar's saying like you don't need thermoclass at all. What you need is to know the chemical, like know the structure, the size of the thing. Say you're gonna have like metal organic, you're gonna limit it to 300 metal kind of cluster things, and then maybe 20 or 30 organic groups that could bond those things. In other words, there's going to be probably a condensation reaction. So you need a kind of a carboxylic acid sticking off of something. So, and that's kind of like all you're going to limit the world to. So you have the size, the shape, and you have the, in other words, is it going to be 1D, 2D, or 3D type shape? And then just those bonding, the reaction of like the hydroxyl reacting with the carboxylic, then that gives off water. So you have that reaction, there's an enthalpy for that reaction. So you feed in, so that's a limited amount of information. You feed that in. In fact, if you're doing just one system, it's just one metal, one organic, and then the shapes and the reactions of those. And those are like the two bricks you're using. You throw those into a kind of a shake and bake thing, and it's going to do the Monte Carlo and assemble the structure that comes out. And then he's going to take that structure that he made, that he says is real, and he's going to put methane in and see if methane sticks to it or not. See if methane will find a hole where it's happy in that thing. And then, so he doesn't include anything about lattice energy, electron gain, electron loss. There's nothing in there. There's no information at all of the framework that's in thermo to talk about heat of formation. It's just this thing. He just lets it pop and then it makes the thing, and that's it. That's all there is to it. So yeah, it's different, you know, it's different than what, like if you believe that, then you probably wouldn't want to, thermo is just going to lead you down the wrong pathway. Like the right pathway would be to find a shape, because you just start with shapes. So like, what shape do I want? And then throw all the possible shapes in and find a shape that you want, not even related to anything real. Then go back and find a molecule that could have that shape. And then make the thing from that, like a backwards kind of making it. And then just throw that in the beaker and see if it self-assembles. Seems like that's not going to work, but maybe it would work. It's just a different approach to do it, I think. So, you know, so it's difference, you know, between the two. I mean, the first, right, neither are probably correct. None of it's probably correct. Everyone is BSing here. Like the thermo people have a long history of BSing. This guy has a shorter history, right? But I mean, basically, there's nobody you can really trust. The only thing you can trust is what you see, and that it works. Then you believe it. But basically, it is kind of based on someone just saying something the same way, you know. somebody just had an idea about heat of formation and then they just went along with it and then it seemed to work. So that's why people use it. So you can't, and then there are these people saying like, so forget about that. I mean, if you come from a computer gaming perspective, then you're used to this idea of things flying around and like sticking and not sticking. And then basically you can think of the world that way. And from that perspective, this makes a lot of sense. Like, yeah, that's how things work. So, but if you're coming from this framework of like measuring the enthalpy of every reaction and adding those enthalpies up and then predicting what the next thing is going to be, this thing doesn't make any sense at all. Right? But neither one is really right. They're both limited by their blinders of what the way they're looking at it. You know? There's probably other ways to look at how to build things, metal organic frameworks or anything else. I mean, so then she's saying at the end in this other paper, she's saying that none of that, like it's not the building blocks, it's not the enthalpy, because the temperature is the temperature is the same as the enthalpy. So the things can get over that energy barriers all the time with just normal room temperature. So none of those things matter. The only thing that matters is that there was clay there, you know, and the clay had these sheet structures and it organized the biological molecules to bond up into sheet structures because there was a clay template for it. And that formed life, you know. That's a different argument from the same person. She's the person that did all the DSC measurements, you know. She's coming back. Yeah, she's the one that I think if you looked at her career, that's what I'm saying. When you looked at her career, she probably started out just doing a lot of DSC measurements. Then she went to this bomb calorimetry. Then she kind of got into this MOF thing. Then she goes to the planet science thing, and all of a sudden it's like the hand of God, you know. Just like forget about all that stuff about enthalpies. It's just like the clay was there, somebody formed the clay, and then the clay made the life. And it came from clay. It came from this templated inorganic molecule guiding the organic molecules to form to make whatever. Right. So that could be right too. I mean, all of it could be right. You know? And there's probably this evidence for each one, you know, but they're different. They aren't the same thing. In fact, she states that the enthalpy part is meaningless. She states it. She says that the temperature is 2 to 3 times, so that the temperature can overcome that 15 kilojoule, making that there's no difference between any of these bonding schemes, right? Because it's basically room temperature. They're all equal energy compared to room temperature. So then in that framework, all these other minor things become more important, and that's what's relevant to the origin of life. Boom. Yeah. There it is. So, and that's in Proceeds of National Academy of Science, which is, that's above Jack's. So we go Jack's, PNAS, then Nature, like in that sequence. So Jack's is going to be like 30, PNAS is going to be like 80, and Nature is going to be like 110 citation index. You know, so basically PNAS is a funny journal though, because if you're a member of the National Academy of Sciences, which is a US organization of like whoever the top people are, then you automatically get a paper in it. Like they can't say no to your paper, they have to publish it. Doesn't matter. So she might be a member of PNAS, and then this paper, they have to publish it, and it goes into the 80 citation thing, like one of the top journals, you know. And also, you can also get a paper published if you're friends with someone who's in the National Academy of Sciences. So they can say like, this paper is good, publish this paper, and then that can get your paper published, or you can submit to it, which is like the normal Joe's way to get into it. Right. So I'd say, so it's 100% if you're a member. It's probably like 80% if you're suggested by a member. And it's probably like 2% if you're a regular Joe. It's a caste system, more or less, you know, whatever. So everyone seems to be happy with it. The journal still gets cited, so no one seems to worry about that. I mean, in effect, like all these journals have some kind of pecking order like that. I mean, there's something like that going on anyway, you know, more or less. I mean,
Is it always like that?
no, I mean, not for all journals. I mean, but for
It
the,
wasn't like that in the past as well.
oh yeah, it was probably worse, you know. I think it was probably worse because it was I mean, originally the journals were all in German, right? Before World War One, I guess, or World War Two. Even after before World War II, all the journals were in German. All the science journals were in German. And the English ones were like not good. There were French journals that were not good. So everything important was published in German. And then like after World War II, like US took over, basically. So then everything was published in English. It was like kind of flipped. And there were still a few things published in French, but not much. And then so now it's like all in English. So basically there was a completely different scheme of pecking order before like 1940. Like, so like the whole journal thing flipped, and then like so it could change again, you know, who knows.
It's like it's not pure meritocracy. Like,
Yeah. Well, I mean, during the Cold War, it was like Russia and the US, you know. It's like we would have like Paul Flory won the Nobel Prize for this polymer stuff. There was a guy, Wolkenstein in Russia, that published almost exactly the same thing. In fact, he published the book that Flory won the Nobel Prize for like 5 years before Flory published his book, and Flory was fluent in Russian. It wasn't published in the US, there's no translation. So some kind of thing that the Russians got upset about that. You know, so and if you look in the Russian books on, at least in polymers, I know every theory has a different name in the Russian book. Like they, so, and who knows who really invented whatever, you know. So yeah, it's all politics. After the Cold War, it doesn't matter, I guess, but basically in that during that time period, it was pretty incredible that you could have the same book published in Russian and English. And the guy in English published it later, won the Nobel Prize for it. That was what was cited in his thing, and it's like not crazy, but anyway. So yeah, that's about it, I guess. For I don't know, there's some other. I didn't go through everything in this chapter, I guess, in the notes, but there's some stuff about heats of formation and the size of the molecules and like substitutional crystals, and it's in the chapter, you know, but it's not really in this homework. You can look at that if you want. It's mostly like people mapping out different impacts on the heat of formation. And I think the authors are interested in this more than it's a topic of interest, you know, but basically the authors are kind of interested in this. Maybe their research was in this, the authors of our book, but it's a little bit of an odd chapter in some ways. Like the atomic size thing definitely is something, like you have to have a match of atomic size to get a crystal to form. This is for perovskites, so the tolerance factor between the components, the two metals that are in it. So if they're one means they're the same size, and then you can get smaller and larger, changes the enthalpy of formation. And the same goes for substitutional crystals, and also interstitial crystals too. So there's size effects with the heat of formation that follow trends. Interstitials, this is like an interstitial solution for crystal where you put another atom into the crystal. Just how that's affected by the size, basically. And same with glasses, heat of formation, heat of mixing has a size effect. So anyway, I kind of mentioned the polymer thing, but yeah, Wolkenstein's the guy that, so this is what Flory won his Nobel Prize for. This Wolkenstein guy published the same thing like 5 years before in Russian. And then Flory published a book, it's almost a duplicate, and he was fluent in Russian, and then won the Nobel Prize for that book on this subject, you know, of calculating the energy of a polymer chain based on this rotation of the bonds, like the energy of rotation. This thing about rotational isomers. Let's take ethylene, you spin it, or butane, and you spin it, butane, and you spin it around, spin the two groups around, you get this energy map for the rotation about that center bond. And then from that, you can calculate the whole chain's energy, right? So we'll talk more about this guy next chapter about the heat capacity. Like talk about the sum of states, some of the probabilities, some of the Boltzmann probabilities for the different states gives us partition functions, examine some, and that's used to calculate the free energy, basically. Like log of that's going to be the free energy. So we get from that free energy, we can get the heat capacity. So this whole thing was based, like Debye and Einstein kind of developed this idea of the partition function. And then Florey used that in his calculation of energy of the chains. But anyway, so yeah, why don't we quit there for today? And yeah, we're going to the power plant today. So if anybody wants to go, I think you guys have conflicts, right? To do tours or anything. But anyway, I got room in my car if anybody wants to go. 3 o'clock, 413 Zimmer is where I'm leave from. But, so